16D, solving problems using the normal distribution. Today we're looking at solving normal distribution problems. So we've already done all of the content that you need to, but we're just going to apply it to applications. So that's what we're learning about, and basically all you need to be able to do is apply these concepts to the normal distribution of various application problems. There's no real things that I can teach you right now in terms of techniques or steps or anything like that. Basically, you just got to read the words, translate it into maths, find the right formulas, and that's pretty much it. There are some specific things that you can do when you come across similar problems, as we'll come across in a little bit, but it's really about just being exposed to as many application problems as you can, so that when you get a question that's quite similar to it, you'll know how to approach it. So let's go ahead and look at a few different types of worded problems and apply all of the things that we've already learned. Example 12. The time taken to complete logical reasoning task is normally distributed. As soon as you see this word, you're thinking bell curve, you're thinking your mean, your standard deviation, everything we've learned in this exercise. It's got a mean of 55 seconds and a standard deviation of 8 seconds. That is the first thing that I would highlight and write down before you even need to continue. Mean 55, standard deviation 8. It's really important that you recognize what kind of distribution you're in and you're able to label those. All right, part A says, find the probability correct to 4 decimal places that a randomly chosen person will take less than 50 seconds to complete the task. A couple of important things. They want us to find the probability and it's 4 decimal places. Please keep that in mind. The key task that they need us to do is less than 50. So for part A, we're finding the probability that we are less than 50 seconds. There's not really much to it other than typing that straight into the calculator. So I'm just going to type in the calculator instructions in green. So in your calculator, you would type in normal CDF. You'll put in your lower bound, which is negative infinity. Upper bound is 50. The mean is 55. And the standard deviation is 8. So you can go ahead and give that a shot on your calculator. These are some ones that I have pre-prepared. I think it's this one over here. So the answer to that is 0.2659, or I guess when I round that, 60. All right, part B. Find the probability correct to 4 decimal places that a randomly chosen person will take less than 50 seconds. So less than 50 seconds. Oh, I'm using too many colors. Here we go, blue, to complete the task if it is known that this person took less than 60 seconds. So just the keywords here, if it is known, which means given. So it's the given probability. So probability that X is less than 50, given that X, was less than 60. So of course, with conditional probability, your top line is what they have in common. So what they have in common is less than 50. So both of them have less than 50, and it's divided by less than 60. So what you'd go and type into your calculator, we'd have normal CDF. Actually, the top one, we already found that, didn't we? You don't even need to type that into your calculator. We already found that in the previous question. Divided by normal CDF, lower bound, upper bound, mean, and standard deviation. And when you type that into your calculator, you should get 0.7340. I'll just confirm that that is the case. Oh, sorry, so that's for the bottom one. I didn't write that out properly, did I? 0.2260, and then you just need to go ahead and divide them through. So that would be 0.2660 divided by 0.7340. Enter, you get 0.3624. Try and remember that number, 3624. Okay, and that's your answer there. Next one, example 13. Limits of acceptability imposed on the lengths of certain battered metal rods are 1.92 centimeters to 5 centimeters and 2.075 centimeters. It's observed that on average, 5% are rejected because they're undersized, 5% are rejected as oversized. Assuming that the lengths are normally distributed, love that word, know where we're at, find the mean and the standard deviation. Now, this is really interesting. We're not used to this type of question. So this application actually does require a specific technique, and once I show it to you today, you'll be able to apply that same technique to similar questions where a mean and standard deviation is unknown. because we've never really looked at questions like this before. I think this question is a little bit strangely worded. I reckon instead of and, it should say to. So metal rods are between those two numbers. So essentially what it's saying is that we're accepting anything as long as it's between these two lengths. Anything outside of that is rejected. So that's this idea that 5% are rejected if they're undersized, so below it. 5% are rejected if they're oversized. Now, my favorite thing to do, as always, draw a diagram. So 1.925 to 0.075. Anything between that, we're good. We're happy with all of this area. Anything outside of that is rejected. So let's go ahead and do that in orange. Rejected, rejected. Now we know exactly how much is rejected. It's that 5%. So this here is 5%. So as a decimal, it's 0.05. And this here is also rejected, which is 5% as well. Now, the thing is, we need to find the mean and standard deviation, and there's no real indication as to where the mean and standard deviation comes in this place. There is one thing that we can use that has both the mean and standard deviation included in it, that is unknown. Now we have, remember, two unknowns, which means we generally need two equations. So the key technique with this is to use your z-score. So what you need to know is that z is equal to your data value minus the mean over the standard deviation. And have a look at that. Here is where the mean and the standard deviation appear. Our data value is, that would just be our regular value here. And then our z-score is whatever value we end up assigning to it, or that we have. So we don't have that quite yet. So how does the z-score play anything to do with this? Well, in this diagram, these values here are x-scores. We can translate them to z-scores. We don't know what they are yet, so I'm just going to call that A and B. So whatever z-curve has this exact same probability, 1.925 will correspond to a certain value A, 2.075 will correspond to a certain value B. If we're able to find these two values, then we can plug it into this formula, this whole formula, and we'll be able to solve for the mean and standard deviation. It's not that simple. There is quite a bit involved, so let's go through what is involved in this. Let's write out the information in terms of what we know. I know that the probability of x less than 1.925 is equal to 0.05. I also know that the probability of x, and notice I'm going to write less than because you might have already guessed it, we will need to use the inverse normal at one point. X is less than 2.075. Well, if that's 5%, then this will all be 95%. Okay, so because the probabilities are the same, whether it's this x-score or this z-score that I'm using, I can rewrite this as the probability that z is less than a certain number, actually because we're using the 0.05, that'll be A, will be 0.05, and the probability that z is less than a certain number is 0.95. So this is the exact same thing, but one of them is in terms of the x-scores, one of them is in terms of the z-scores. So, whoops, I did not intend that. I intended this, the yellow highlight. Now we might be at a point where you might think that this is familiar. How do I find, given the probability, how do I find this score? Well, yes, it would be the inverse normal, which is what we learned in the previous exercise. So we would go inverse normal, the area, which is 0.05, the mean and the standard deviation. And I can use it because I know the mean and standard deviation of the z-curve, which is always 0 and 1. I'm going to do the same thing here. So that would be 0.95, 0, and 1. So go ahead and try that onto your calculator. Once you get it, you'll notice that you get negative 1.64 and positive 1.64. No surprise there that they are equivalent. Okay. So what can we do with these values? Well, if this is the z-score and this is the x-score, can I not plug them into here and find my unknowns? I have two equations and two unknowns, and then I can go ahead and solve it from there. So I'm just going to create another page. We can then write, so I'll just quickly rewrite the formula for you there. Now our first z-score that we got was negative 1.64. that corresponded to the x value of 1.925 minus the unknown mean and the unknown standard deviation. My next z-score that I got was 1.64. That corresponded to the x value of 2.075 minus the mean over the standard deviation. Now I essentially have two equations. I can go ahead and type these into my calculator and solve for the mean and standard deviation. Now, I probably wouldn't go ahead and use mean and standard deviation in the calculator. We'd probably want to use S or M or X or whatever you want to use. All right, so you go ahead and do that. At the same time, I'm going to do the same. So we'll do two equations. I'll use M for the mean and S for the standard deviation. All right, so our first equation was negative 1.64 is equal to data value 1.925 minus the mean on the standard deviation. Next one we had was 1.64 equals corresponding x value 2.075 minus the mean on the standard deviation. When you press enter, hopefully it gives you a really nice answer. So we've got the standard deviation is 0.0457 and the mean is 2. So again, I'll try and remember these numbers. The standard deviation, I've already forgotten it, 0.0457. Oops. 04. I think it was 57. If not, I'll change it in a sec. And the mean was very kindly 2. There we go, 57. Beautiful. So that there is how you would go ahead and you would find that mean and standard deviation. It is a very specific technique that you need to use, the z-score, and it's just something you need to practice. But now you know whenever you have an unknown mean and standard deviation, this is the technique that you're going to do. We're going to go ahead and do pretty much the exact same thing with this situation. So I would recommend you pause the video and give it a go yourself and then follow along as I go through it. The height of an adult giraffe is normally distributed. So again, we've got the normal distribution. If 5% of giraffes are more than 8 meters tall, but only 10% are less than 6 meters tall, find correct two decimal places, the mean and the standard deviation. I actually didn't check in the previous question if it told us how many decimals. No, it didn't. In this case, it's very specific to 2. All right, I'm going to write down the information I've got. So probability that x is less than 8. So if 5% of giraffes are more than 8, that's 5% of that happening. We also have, we've got, but only 10% are less than, that was silly, less than 6 meters tall. The 10% is the probability, so that's 0.1. Find the mean and standard deviation, and we know in order to do that, we must use our z-score. All right, to do that, what we're going to go ahead and do is convert these into the z-score, and then we can plug them into the formula. And of course, I'm going to go ahead and draw a diagram because I love diagrams. I think they're very important. So what we know is that at this value 8, above that is 0.05. That area there is 0.05. We also know that below the value of 6 is 10%. So that there is 10%. That is our x scores. Our z scores are A and B. We don't know what they are. They correspond to some sort of value where it has the same probability. So let's go ahead and try and write it in terms of A and B. Now, there's two things that are going to happen at the same time. The first thing I'm going to do is write it in terms of Z, and A would correspond to B. But because I know I'm going to use the inverse normal, remember inverse normal is always from infinity to the value. So I need to use this section, not this section. So I know above 8 is 0.05, but because inverse normal always works with below, that's going to be equal to 0.95. So I want Z less than B is 0.95. This one's a little bit easier. Z less than A is 0.1. So it's the same probability. I'm just trying to figure out what is it in terms of z. Here, different probability only because when you do the inverse normal, it has to be the less than part. But it's still the same value, just one's on the x distribution and one is the z distribution, which is your standard score. All right, inverse normal. So into your calculator will go inverse normal, the area, the mean, the standard deviation, and same thing here. Mean, area, mean, and standard deviation. Now I have not pre-prepared this one, so I will have to go ahead and type that into my calculator. You do the same. All right, so inverse normal. We'll go to probability, distributions, inverse normal. So my area is 0.95, standard deviation of 0 and 1, that's 1.664. It's a familiar number to before. Sorry, was it 664 or I think it was 644, but we'll just do it to 2 decimal places. So what this is telling me, I'm just going to raise this up a little bit. When x is 6, the corresponding value, when x is 8, the corresponding value is 1.64. And now we'll have a look at what it is with a. So just copy and paste that. This time though, the area was 1. That's negative 1.28. Alright, so that's your corresponding values. So these are our z scores, which go into here. These are our x scores, which go into here. And then what we are trying to find are our mean and standard deviation. So from there, I'm going to go ahead and set up my two equations. So when I have a z score of negative 1.28, that corresponds to an x score of 6. So that's all together, minus the mean and standard deviation. When I have a z score of 1.64, that corresponds to the x value of 8 minus the mean and standard deviation. That can go onto your calculator, just like we did previously, and when you do that, you get the mean is equal to 6.88 and the standard deviation is equal to 0.68, both correct to 2 decimal places. All right, last example. So bolts are produced on a particular machine, have a diameter which is normally distributed, our favorite words, with a mean of 10 millimeters and a standard deviation of 0.2. So I hope you're getting into the habit. This is the first thing that I would always write. Find the proportion of bolts that have a diameter of more than 10.5 and between 9.9 and 10.1. So this is just as simple as plugging it into our calculator. So for part A, I'm wanting the probability of x being greater than 10.5. At this point, hopefully this is very normal for you. Normal, see what I did there? 10.5, infinity, 10.2. You should get 0.0062 to 4 decimal places. And for part 2, probability of 9.9 to 10.1. CDF will be 9.9, 10.1, 10.2, and that'll be 0.3829. Okay. Now, this is the part that's a little bit more exciting or different. A bolt is accepted and hence sold if its diameter is between 9.9 and 10.1. Out of 10 bolts produced by the machine, find the probability all are accepted and then at least half are accepted. So the wording changes here because it's not about what is the diameter or how big is it. It tells us it's accepted if it's this. And then the other option is that it's not accepted. But that's kind of your two options here. So hopefully you can see this is actually not the normal distribution anymore. We've now stepped into binomial because it's either accepted or it's not. So your success is accepted and then your failure is being rejected. Now, what does binomial have to do with this? Well, part of binomial is the probability. And the idea is that it's accepted if it's between 9.9 and 10.1. So the probability of success is something we previously found, which is between 9.9 and 10.1. So that's how the two relate. If we've previously found the probability, then that becomes the probability of success of this option happening. So we did find what the probability is, that it's between 9.9 and 10.1. That's 0.3829. So that's the probability of success. And now we can use our binomial distribution from there. The other bit of information that we need, of course, is the number of trials. So in this case, we've got n is 10 trials. So here we can actually write up our binomial distribution. So we've got 10 trials with a probability of 0.3829. So we do not need to use the normal anymore. We're now in binomial only. Now, if all of them are going to be accepted, we want the probability that x is equal to 10. You can chuck that straight into your calculator, into Binom PDF, where we've got the number of trials of 10, the probability of success is 3.829, and we want 10 successes. When you put that into your calculator, you get 0.000068. So usually I would write it to 4 decimal places, but that's really not going to help us out in this case. For part 2, very similar. Now we want probability is x's greater than or equal to 5. We want at least half to be accepted. So now, because we have accumulation of it, we're in binom CDF. We have 10 trials. We have 0.3829 probability of success. The least number of successes I want and the most successes I want is 10. When you type that into your calculator, you get 0.3247. This is a very common thing to happen. We start off with the normal distribution to find the probability, and then it turns into binomial. So have a look out for it, and it's usually just this kind of wording about it will be accepted, which indicates that there's only one other option of it not being accepted, whereas the wording here, first of all, says very clearly the normally distributed, but it's also between an interval. There's no such thing as an interval with binomial. It's also out of whole numbers, whereas here it's very clearly out of decimals. That's it for exercise 16D. I know it's a big one, but this is really what your exam is going to be all about. So please practice it and let me know if you have any questions.